In this video, we'll discuss rhombi and squares. Now, previously we discussed the parallelogram, which is a specialized quadrilateral where the opposite sides are parallel and congruent, and we know the diagonal interior angles are also congruent, and then if we construct the diagonals, they will bisect each other inside the parallelogram. We also discussed the specialized parallelogram of a rectangle, which has 4 right angles. Let's look at another specialized parallelogram, the rhombus. The rhombus is unique in that all sides will be congruent, and by doing so we get unique properties related to the diagonals. They will still bisect each other, but they're now going to be perpendicular, and they will become angle bisectors of the larger angles of our rhombus. This constructs 4 congruent right triangles inside the rhombus. So let's look at rhombus BDAC. Here we're just looking at the larger angles and wanting to know what are the other 3 angles if we know angle C measures 72 degrees. Just like a parallelogram, the opposite angles are congruent. So angle B becomes 72 degrees. Angle B and C are supplementary, so angle B would have to be 180 degrees. And then B and A are going to be congruent angles, so A must measure 108 degrees. But what if we construct in the diagonals? Now we also have to change this so we don't say just angle C, we have to say angle ACB is the larger angle because multiple angles share that vertex. But we recognize that when doing so, we are bisecting each of those larger angles. So to determine ACE, we just have to divide the larger angle in half, and that'll give us 36 degrees. And if ACE is 36 degrees, we know that BCE will also be 36 degrees. Now this is helpful because we're looking at now this right triangle, and we know that in a right triangle, the interior angles must measure 180 degrees in their sum. So if we subtract 90 and 36 from 180 degrees, we'll get 54 degrees for angle EBC. And if you think about the larger angle we just discussed, it was 108 degrees. 108 divided by 2 is 54 degrees. Now what if we were talking about the sides instead? So here, maybe we'll find BC, DE, and AB if we know that segment DC is 16, and on the image we're marked as having the exterior side being BD as 10 units. So first, let's remember that the diagonals bisect each other. That's just helpful to remember as we're looking at all these images. Now let's start to figure out what we have. We know the outside is all 10 units, so if BD is 10, we know BC is 10, just like AC and DA would all be 10 units. Now for DC, if we look at our image after we've marked it, we can see it's split into 2 congruent segments. So what that means is we can divide DC in half and know that DE would have to be 8 and EC would have to be 8. Now, as we look then trying to figure out AB, it's kind of hard to figure out this, but what we have to remember is we have this right triangle. And in a right triangle, we can use Pythagorean theorem to find the missing side. So in this case, we know that BE squared plus ED squared plus equals BD squared. So now we know that the missing side BE squared will equal 8 squared plus 10 squared. And now that's 64 and 100. We're going to subtract 64 from both sides, and then take the square root, which will mean that BE is 6 units, which means that EA is 6 units since they are congruent. Therefore, AB has to be double that, which is 12 units. Now let's look at our special quadrilateral, the square, which is a parallelogram with 4 right angles and 4 congruent sides. So it's the combination of the rhombus and the rectangle. By doing so, we're going to have diagonals that are congruent and they bisect each other. In other words, what's going to happen is we're going to have 45, 45, 90 right triangles inside. In other words, we can use all those properties of that special right triangle to help us find missing sides. So say we have this square here where we know that MN is 8, and we want to find the other sides in missing diagonal pieces. We know that the diagonals will be congruent, so when I have this, I know that MP has to equal 8, and then I can look and say, well, each of these are 45, 45, 90 triangles inside. But if I can't remember those properties, I can use Pythagorean theorem. What I want to recognize is that Rn and Mr are the same measure, so I can just double Mr squared to give us that side. So then I'll have 2 times Mr squared equals 64. Divide both sides by 2, and then take the square root. And remember, when we take the square root of 32, we want to simplify that as far as possible, which is 4 to the square root of 2. And if we think back to special right triangles, if we take the side, we know the hypotenuse is that side times the square root of 2, which would give us 8. Now we know then that MR and RL are both 4 square root of 2, which means that ML is the sum of those two, which is 8 the square root of 2. Now the last thing I want to talk about is the classification of quadrilaterals as a Venn diagram. In the large group, we have quadrilaterals. That's all of our closed four-sided shapes. The next specialized group that we have inside there are parallelograms, which have the opposite sides being parallel and congruent. Within this specialized group, we have both the rectangles and the rhombi, and then inside their intersection fall the squares. And we can use this Venn diagram to help us always think back to the most restricted versions we have upwards. So a parallelogram can split off into rectangles and rhombi if they have those properties, but they come back together to make the square. Now let's use these to help us answer a few questions. What quadrilaterals have congruent opposite sides? Well, we know that starts at the parallelogram, so anything inside. So that's the rectangles, the rhombi, and the square, all of them because they fall inside the parallelograms. What about four right angles? Well, we know that's a unique property of rectangles, but squares is inside that group, so it's both of those. Does there exist a rhombus that is not a parallelogram? Well, the entire rhombus is inside the parallelograms, so no. And lastly, can a square be a rectangle but not a rhombus? Well, no, because the square is always inside that rhombus category as well. So we can use this to help us understand those relationships and what makes them unique as well as similar to one another.